At the end of this video, you should be able to relate the motion of a freely falling body to motion with constant acceleration, calculate displacement, velocity, and time at various points in the motion of a freely falling object, and compare the motions of different objects in free fall.
A falling object accelerates at a constant rate due to the force of gravity. As the object falls, the velocity will increase at a constant rate. The free fall acceleration due to gravity, symbolized by the letter g, is 9.81 meters per second squared at the Earth's surface. If only the force of gravity is acting on the object, then the motion is known as free fall. Air resistance is a force that slows a falling object. That is why a falling object can only be in free fall if it is in a vacuum. If an object like a spacecraft is in free fall, the occupants inside will also be in free fall and appear to float.
Chapter 2, Section 3, Falling Objects. On August 2, 1971, a demonstration was conducted on the moon by astronaut David Scott. He simultaneously released a hammer and a feather from the same height above the moon's surface. The hammer and the feather both fell straight down and landed on the lunar surface at exactly the same moment. Although the hammer is more massive than the feather, both objects fell at the same rate. That is, they traveled the same displacement in the same amount of time. In the figure on your screen here, a feather and an apple are released from rest in a vacuum chamber. The two objects fall at exactly the same rate, as indicated by the horizontal alignment of the multiple images. The amount of time that passed between each successive image is the same. However, as shown in each picture, the displacement of in each time interval did not remain constant. Therefore, the velocity was not constant. The apple and the feather were accelerating. Compare the displacement between the first and second images to the displacement between the second and third images. As you can see, within each time interval, the displacement of the feather increased by the same amount as the displacement of the apple. Because the time intervals are the same, we know that the velocity of each object is increasing by the same amount in each time interval. In other words, the apple and feather are falling with the same acceleration. If air resistance is disregarded, all objects dropped near the surface of a planet fall with the same constant acceleration. This acceleration is due to gravitational force, and the motion is referred to as free fall. The acceleration due to gravity is denoted with the symbol a sub g, generally, or simply lowercase g, as on Earth's surface. The magnitude of lowercase g is about 9.81 meters per second squared, or 32 feet per second squared. Unless stated otherwise, this book will use the value 9.81 meters per second squared for calculations. This acceleration is directed downward toward the center of Earth. In our usual choice of coordinates, the downward direction is negative. Thus, the acceleration of objects in free fall near the surface of Earth, which is to say a sub g, is equal to negative g, which is equal to negative 9.81 meters per second squared. Because an object in free fall is acted on only by gravity, a sub g is also known as free fall acceleration.
In the 16th century, Galileo theorized that if there were no air resistance, all objects would fall with the same acceleration. Let's drop two objects into a room that has had all the air removed. A camera and a strobe light reveal that the two objects move together at all times. Notice also that the two objects move a greater distance during each time interval. The distance between two successive images is proportional to their velocity during that interval. So you can see here that the downwards velocity is constantly increasing. In a full second of fall, the velocity will increase by 9.81 meters per second. The acceleration caused by gravity near the surface of Earth is therefore 9.81 meters per second per second.
The figure on your screen here is a strobe photograph of a ball thrown up into the air with an initial upward velocity of positive 10.5 meters per second. The photo on the left shows the ball moving up from its release toward the top of its path, and the photo on the right shows the ball falling back down. Everyday experience shows that when we throw an object up in the air, it will continue to move upward for some time, stop momentarily at the peak, and then change direction and begin to fall. Because the object changes direction, it may seem that the velocity and acceleration are both changing. Actually, objects thrown into the air have a downward acceleration as soon as they are released. In the photograph on the left, the upward displacement of the ball between each successive image is smaller and smaller, until the ball stops and finally begins to move with an increasing downward velocity, as is shown on the right. As soon as the ball is released, with an initial upward velocity of the positive 10.5 meters per second, it has an acceleration of negative 9.81 meters per second squared. After 1.0 seconds, meaning delta t is equal to 1.0 seconds, the ball's velocity will change by negative 9.81 meters per second to 0.69 meters per second upward. After 2.0 seconds, meaning delta t is equal to 2.0 seconds, the ball's velocity will again change by negative 9.81 meters per second to negative 9.12 meters per second. The graph shown on the screen here shows the velocity of the ball plotted against time. As you can see, there is an instant when the velocity of the ball is equal to 0 meters per second. This happens at the instant when the ball reaches the peak of its upward motion and is about to begin moving downward. Although the velocity is 0 at the instant the ball reaches the peak, the acceleration is equal to negative 9.81 meters per second squared at every instant, regardless of the magnitude or direction of the velocity. It is important to note that the acceleration is negative 9.81 meters per second squared even at the peak where the velocity is 0. The straight line slope of the graph indicates that the acceleration is constant at every moment. It may seem a little confusing to think of something that is moving upward, like the ball in the example, as having a downward acceleration. Thinking of this motion as motion with a positive velocity and a negative acceleration may help. The downward acceleration is the same when an object is moving up, when it is at rest at the top of its path, and when it is moving down. The only things changing are the position and the magnitude and direction of the velocity. When an object is thrown up in the air, it has a positive velocity and a negative acceleration. From the table on the screen here, we see that this means the object is slowing down as it rises in the air. From the example of the ball and from everyday experience, we know that this makes sense. The object continues to move upward, but with a smaller and smaller speed. In the photograph of the ball, this decrease in speed is shown by the smaller and smaller displacements as the ball moves up to the top of its path. At the top of its path, the object's velocity has decreased until it is 0. Although it is impossible to see this because it happens so quickly, the object is actually at rest at the instant it reaches its peak position. Even though the velocity is 0 at this instant, the acceleration is still negative 9.81 meters per second squared. When the object begins moving down, it has a negative velocity, and its acceleration is still negative. From the table on the screen here, we see that a negative acceleration and a negative velocity indicates an object that is speeding up. In fact, this is what happens when the objects undergo free fall acceleration. Objects that are falling toward Earth move faster and faster as they fall. In the photograph of the ball, this increase in speed is shown by a greater and greater displacement between the images as the ball falls. Knowing the free fall acceleration makes it easy to calculate the velocity, time, and displacement of many different motions using the equations for constantly accelerated motion. Because the acceleration is the same throughout the entire motion, you can analyze the motion of a freely falling object during any time interval. At this point, you should be able to attempt sample problem F.
Let's toss a ball into the air and think about its velocity and acceleration as it travels. When the ball is first tossed into the air, it is moving quickly upwards. It slows, then changes directions, and speeds up again on the way down. Let's look at this again and focus on the velocity. Suppose the initial upwards velocity is 20 meters per second. As the ball travels upwards, the velocity slows. Let's freeze the motion at the top. At this point, the ball is no longer traveling upwards, so it does not have a positive velocity. However, it has not yet started moving downwards, so it cannot have a negative velocity either. The ball must therefore have a velocity of 0. Next, the ball starts to descend and gains speed as it travels. Let's throw the ball one more time and graph its velocity as a function of time. As you can see, the velocity changes smoothly from upwards, positive, to downwards, negative. Remember that acceleration is the slope of the graph of velocity versus time. You can see that the velocity graph has a constant negative slope. This slope is the acceleration due to gravity, negative 9.8 meters per second squared. The ball has this same acceleration at all times, even as its velocity is positive, then briefly 0, then negative.
At this point, you should be able to relate the motion of a freely falling body to motion with constant acceleration, calculate displacement, velocity, and time at various points in the motion of a freely falling object, and compare the motions of different objects in free fall.